Hello, my name is Abby J, and I'm going to be talking to you for the next hour or so about an important work post-processing tool called NCL. So the NCAR command language was developed here at NCAR, and it can be easily accessed and downloaded here at www.ncl.ucar.edu. One of the really great things about NCL is that it reads your WRF-ARW data directly, unlike some other post-processing programs where you need to post-process your data to put it into post-process again, which is highly inconvenient. NCL can also generate many types of graphical plots, including horizontal, cross-sections, skew-tees, mediograms, and panels. And I'll show you a lot more examples in the next few slides. So here's some example plots to just show you what kind of plots NCL is capable of making. It can make some simple contour plots, some raster plots. It can do cross-sections of terrain height and relative humidity, vertical cross-sections that show terrain in there. And also it can do horizontal cross-sections as seen in the lower right-hand corner of surface temperature. Some other examples here are skew-T. The skew-T plots are fairly simple. You just need to give NCL the latitude and longitude or the grid cell that you're interested in, and it'll give you a vertical profile like so. You can also do a domain overlay. So if you want to include your larger domain and your smaller domain, but keep the resolution of your smaller domain, you can overlay it on the larger domain. Also time series plots and more complicated plots such as a windrows. A few more examples are you can easily track a storm track, which I'll show later in the presentation, as long as you have the latitude and longitude markers of your track. You can also make a bar chart and a Taylor diagram. Some example plot functions are that you can zoom in on a specific feature, such as a hurricane in the left, and you can also make panel plots very easily. A really good place to start in generating plots is a WRF online tutorial for using NCL. It'll show you how to make all of the plots that I just showed in the previous example slides. It includes all of the scripts that you need and a place where you can download dummy data to make these plots if you don't want to use your own data. These are all really great. I really recommend starting with a script that's already been written and making changes in it to fit what you want it to do. To download NCL, you just go to the following website. You will need to fill out a short registration form. There's a short waiting period. It's usually less than 24 hours. You need to read and agree to an OSA-based license. And we highly recommend getting version 6 or later. The current and latest version is 6.6.2. If for some reason you have an earlier version, I'm going to show you in a few slides some very specific things you'll need to do to get it working correctly. And I always recommend downloading the binaries code instead of the source code so that you do not have to compile it. I'm just going to show you really quickly how the NCL and the WRF-specific libraries work together. So to start out, on our left, we have NCL libraries, and then we have WRF-specific libraries. These WRF-specific libraries are put in a script, which is easily accessed and downloaded with your NCL binary. It's WRF-user-arw.ncl. And then we also have diagnostics like sea level pressure. These are maintained and supported by the WRF development group, and they are also user modifiable. So if you want to add something or change something you don't like how it's calculated, you want to use a different version of the calculation, you can go in and change that. So if you do happen to have or only have downloaded an NCL version earlier than version 6, or say you're a grad student and you're using a very old computer in the lab, these are some important documents that you might need to look at. This file is very important. We call it the HLU res file. It must be placed in your home directory, and it controls your color table, your font, the white and the black background, the size of the plot, and certain characters. You also need the set NCAR-GROUP environment variable with the set env command, and we want to ensure you have that HLU res file. And next we're going to create a script, which I'll walk through. Most of the WRF script routines are called from that WRF user arw.ncl file, and again, you can add or change the script very easily. And finally, to generate a plot, you'll just want to run your NCL script. And it's very easy to run NCL script once you have NCL installed. All you need to do is type NCL and then the name of your script. All right, I am going to walk through how to create a plot and how to write a very simple NCL script to do so. This is a basic outline of how you create an NCL script. You will start out by loading your NCL library scripts, and then the bulk of the script will be between a begin and an end. And you will open your files, you'll open the graphical output, you'll read your variables, and then you'll set up the plot resources, and then you will output your graphics. I'll go through these specifically now. This is how you would want to load your NCL libraries. This load is not required if you are using an NCL version of 6.3 or later, but if you are using a previous version, you will want to make sure you have these load lines. Also, if you choose to change your WRF user arw.ncl file, you will want to load that from your personal directory that you are storing that script in. And this must be loaded. If you want to use your own specific script, this must be loaded no matter what version of NCL you're using. All right, next we're going to open our file with this function called add file. It's really obvious. So with this add file, we can we'll put down the name of our file, and in this line, we're saying that we're going to read the file, but we can also open it as W, which is for write, which will give you the capability of overwriting variables in that file. And then also, if you are creating a new file, you can mark that with a C for create. One more thing I would like to point out on this file name is that if you do an ls of all your WRF-out files that you've created so far, you'll notice that they don't have a .nc on the end of them, even though they are netcdf files. The thing about NCL is that it doesn't know unless you specifically tell it that it is a netcdf file. So what we want to do is we just want to put the name of our WRF-out file and put .nc at the end. So NCL specifically knows what type of file we're looking at. Next, we're going to open our graphical output. So we open a graphical workstation. And with this X11 that I have here, we're just going to write it to the screen. It's going to open up a window on your computer. And also we're going to name this plot _surface. You can either output this on the screen, which I explained just now with an X11 window, or as a PDF, an EPS, a PS, a PNG, or a CGM. I always write my plots to an EPS, and then I use a file converter EPS to JPEG to put it in a high resolution JPEG file. Next, we're going to read in our variables. So we're going to use this really very useful function called WRF user getvar, and we're going to point it at the file A, which we read in with the add file function. We're going to read in T2, and we're going to read in the first dimension. Not the first dimension, the very first time, I'm sorry. What's really important to note about NCL, that it is a zero-based language, so everything starts at 0, 1, 2, 3, and Fortran starts at a 1, 2, 3, 4. Here are some different ways to read in T2. So using the WRF user getvar, we'll point it at file A, T2, and we want to read time 0, which is the first time. Another way to read it is we can say A pointing at T2, and since time is the very first dimension, we'll say 0th time, and then both X and Y dimension. If we want to read all the times, here's an example of how to do that using WRF user getvar. We point out the file A, say T2, and then the -1 will read all of the times. If you don't want to use the WRF specific, you can say A point to T2, and that's it. It'll read in everything. I just want to go into more specifics about the WRF user getvar. It's really a very useful function. It can read fields directly from the file, such as we have an example here of height and T2. So those are output variables from WRF. However, sea level pressure is not output in WRF. And instead of you writing a function to calculate that in NCL, WRF user getvar will calculate it for you if you type in SLP. This is why you really want to use WRF user getvar for your WRF data. We have all these different diagnostics that are really very useful. So for example, you can output absolute and potential vorticity, CAPE, cloud top temperature, pressure, sea level pressure, dew point temperature, potential temperature, all of these things that are not necessarily direct WRF outputs, but NCL can calculate them with this function. Next, we're going to set up our plot resources, our map resources, and our plotting options. So our plotting resources are things we can set up like overlays over a map. A map resource, which I named MP-res here, you can name it whatever you want. We'll focus on the map resolution and zooming into the map if you so desire. And the options are the resources that are associated with each individual plot. So for this example, we're saying that we want contour filled on. We're saying that it will equal true, which turns it on. Next, this is where we output our graphics. We're going to use the WRF specific function called WRF contour. And what we input into that function is we're going to point it at file A so that it can get all of the domain information from your WRF file. We're going to write it to the workstation that we opened. We want it to look at T2 and do contours for T2. And then we're saying options, which we know that we set our contour fill for on. Next, we say we're going to plot it over a map. If you don't do WRF map overlays, it won't plot it on top of the map and you don't really know what you're looking at. So we're going to use the function WRF map overlays, and we're going to point it at our file A again and our workstation that we opened, and we're specifically going to plot contour underscore T2, which we made with the function of WRF contour. And then we're going to point at our plot resources and our map resources so that everything works out how we want it to. And then we will get a plot like this. The only specific thing we did for this plot was set our contour fill on, which we set to true, but we could also, using our map resources and our plot resources, change, for example, the grid line color or the color of your boundaries or whatever. We can make these plots look specifically how we want them to. And also, what if we wanted to also include sea level pressure contours on top of this map? How we would do that is we would add these lines in blue. So first we'll read in sea level pressure. We'll use WRF user getvar as a diagnostic to calculate sea level pressure. And then we'll set some more plot options. We will set our options for the sea level to a contour line color. So instead of a filled contour, we're going to do line contours, and we're going to say we want to color in blue lines. We're going to use WRF contour again to make a contour sea level pressure. And then we're going to use WRF map overlays again, pointing at our file A and our workstation. And then as you can see here, we're plotting both contour underscore T2 and contour underscore SLP and pointing it at our plot resources and our map resources. And we will end up with a plot that looks like this. So we have our temperature with the filled contours and our sea level pressure with the blue lines. Next, I will talk about some specific WRF NCL functions. We already learned a lot about how WRF user getvar works and WRF contour in the previous examples. There is also a WRF vector, which will really easily calculate and draw some vector plots. We already saw WRF map overlays, and there's also a WRF overlays to overlay over something other than a map. We also have WRF user interp 3D, which you can use to interpolate horizontally to a given pressure or height, like 500 millibars, which is only useful with 3D data only, and WRF user interp 2D, where you can interpolate vertically along a given line. Another really useful function is WRF user LL2IJ, that stands for, or 2XY. That stands for latitude and longitude to XY, which is a specific grid point in your domain. With this function, you can just type in a latitude and longitude and they'll give you that grid point. And we also have the other way around, XY to LL. We also have WRF user unstagger, which will unstagger an array such as your winds. And then we also have a newer vertical interpolation routine or function called WRF user vert interp, and I will show some detailed examples of that later. There are also a few functions that can be really useful where we have WRF WPS read int and WRF WPS write int, and these are for the intermediate files that you create with the WPS program. If for some reason you want to check your intermediate files or write new ones to create updated inputs, you can use these functions in NCL to do so. So one great thing about NCL and WRF NCL is that we can combine the strength of both of them to make some really amazing plots. On the left here, we can see that we can use WRF map overlays with the plot resources and the map resources, which we saw. But I can just show you some of the map resources we can set, such as grid spacing. You can say every 45 degrees. We can also set geophysical line colors, grid line colors, national line colors, US state colors, and also like which kind of boundaries we wanted to draw. And on the right, we'll just see that we're using add file to open up a WRF out file. And then here's a few examples of how you can read them. So this first example here shows that we're reading in time 5, and that's just we're pointing directly at T2 because we know it's a WRF output, and then also a way to use the WRF user getvar to do the same thing. Q vapor, which is a 4-dimensional output variable for time 5, goes like this. If we want to read T2 for all the times, we just point at T2, or with WRF user getvar, we read in T2 with a -1, which reads all the times. WRF user getvar can also be really popular if you don't want to read just one time or all the times. You can use it to say, I want to read from times 0 to 10 every second time. Or you can just say, I want times 1, 2, 3, 4, 5. So I'm going to drop the first time and then all the other, and drop the times after 5. So that's like a really useful way to use WRF user getvar to read in your times. These NCL resources are also quite popular. They're a way to make your plot look exactly how you want with the map resources or the plot resources. So these are all specific. They're not specific functions, but I'm trying to think of the word. They're groups of functions. So there's all kinds of contour functions, there's map functions, there's vector functions, there's XY plot functions. So this website that I have linked to will be very useful for you to specifically make the plot look how you want it to. All right, next we're going to talk about how to specifically use WRF user vert interp, which is the newer vertical interpolation function for your WRF data. With this function, we can interpolate to pressure, grid point height at mean sea level, grid point height at above ground level, potential temperature, and equivalent potential temperature. So one important resource that you might want to set if you want to extrapolate below the ground is ops at extrapolate, and you would set that equal to true. One reason you might want to use this is if, say, you're interpolating to a pressure level at like 900 and you have some terrain in there where the terrain is actually below 900 millibars, so you're not going to have any data there. If you want to fill that in without it looking too wonky, you can extrapolate below the ground, but we really don't recommend doing that unless it's only like a few grid cells or something, because that data doesn't really exist. Here's an example of a script of how to use that. We'll start out by typing begin and adding our WRF-out file using add file. Next, we're going to read in temperature in Kelvin with WRF user getvar just at the first time. So we're going to set our vertical coordinate to pressure. This is the surface we want to interpolate to. And then we're also going to set our levels. We're going to interpolate to levels of 200, 300, 500, and 1000 millibars. So we're going to set our options to true, and we're going to extrapolate below the ground, which we have set to true. Next, we're going to use our function of WRF user vert interp. So we're going to give it our WRF file, the variable that we read in, the vertical coordinate that we're going to read is pressure, and the levels that we want to read, and also the options that we want to look at. Next, we're going to open our workstation. We're going to print it to the screen, but we're also going to name it plot underscore TK underscore 1000 millibars for when we change that to actually making our plot an EPS or a PDF or something. So we're going to set our options for the plot. We're going to turn them on, and we're going to say that we want our contour fill on to be true. And then we're going to set some map resources. We want our geophysical line color to be black instead of the default of white. So next we're going to make the contour and plot it over a map. Our contour here, we're going to use the function WRF contour, and we're going to contour the interpolated variable that we made, tk underscore interp. So we're going to plot it, we want to contour it at time 0 and at level 3. So if we look at interp levels, if we count 0, 1, 2, 3, that's going to be 1000 millibars is what our plot is going to contour to. And we point to our options, ops 2. Now we're going to plot it using WRF map overlays and our contour variable that we made. And we're going to get a plot that looks something like this. A very nice temperature plot over the UK. All right, next I'm going to talk to you about a really useful function that I use all the time called WRF user LL2XY. This stands for latitude longitude that you input, and it will output the XY point of your latitude and longitude that you input. I'm just going to show you a quick example here. We're going to set our resources to true. We're calling them lat-lon resources. And we're also going to say llres at return int equals false. So it's not going to return an integer. Now we're going to name our output variable locxy, and we'll call the function WRF user ll2xy. We're going to point it at our WRF file that we read in. Then we're going to give it the longitude and then the latitude and point it to those resources that we set. What comes out of that is 17.95 and 59.48. This can be useful if you want to know where exactly in the grid point it is, but it's really not useful if you're wanting to pull out data from a specific point in the model, because if you give this information to the WRF model, it won't know what it's looking at. So we actually want integers. So what we can do is we can change return int to true, and that will spit out the corresponding closest grid point to your latitude and longitude, which in this case is 18 and 59. One thing that's also really important is you need to be aware of the size of your domain and what latitude and longitude points are outside of your domain. So in this case, we put in a longitude of -95 and a latitude of 25. These are, however, outside of our domain. So since they're in the far left corner, it's going to return negative XY point. And it's pretty clear that it's outside of our domain. However, if we choose a point, a latitude and longitude point that's outside the domain, like in the upper right-hand corner here, it's going to spit back 68 and 87, and you need to really be aware of the size of your domain, which the size of our domain here is maximum 60 and 73. So it's just like really important to keep in mind. Here I'm going to show you how we can use that lat-lon2xy function to pull out some time series data. So here we're going to use that function of locxy equals WRF user ll2xy. We're pointing it to our WRF data and our longitude and our latitude. And it spits out a two-dimensional variable, and we're going to say locx equals locxy of 0, and locy is locxy of 1. So we're going to pull out t2 at that point. So we're going to name our new variable t2 point. We're pulling it out of file A, and that first colon in the time dimension, we're going to pull out all the times at the 1 point of loc-y and loc-x. Now we can just use a very basic NCL XY plotting function, GSN CSM XY, pointed at our workstation, our times, and the T2 point and the resources that we set, and it'll push out a plot that looks something like this. However, if we want to use WRF user getvar for one of our diagnostics, such as sea level pressure, we need to add an extra step. So we'll calculate SLP using WRF user getvar, reading in all the times, and then we'll make a new variable called SLP point, and we'll say that equals SLP all the times with that colon, and then the location of your y and x, and then SLP plot the same way we did the T2 plot. One thing that's really important to talk about, and will be talked about in the domain presentation and this tutorial as well, is that NCL has a way to look at your domain. So we wrote a script called plotgrids.ncl, which is available in your WPS download. And what you will want to use it for is to test your domain. It reads your WPS name list, and it will print out a plot just like this that will show you what your domains look like. As you can see from this plot, this domain design is quite terrible because there are domains on top of domains. And this will give you like a really easy red flag that you need to like rethink your design before you get too far, even running WPS, even running GeoGrid, for example, in WPS and Real and WRF before your model would blow up on you. Next, I'm going to show a further example of how we can overlay domains to be useful and easier to look at. Here's an example of Hurricane Katrina in a moving nested run. So this is a WRF run, and all we did was plot the moving nest in a loop. This is really hard to see and make sense of what's really going on in the way that it's created here. So what we can do is we can overlay it onto a larger domain so that it's much easier to see, understand what's happening, see exactly where the landfall is happening, and also how the storm progresses. In this next slide, we're going to see how we can change fields directly in a netcdf file. So what this slide is going to do is, say we're doing a pseudo global warming run, and we just want to add a number to the SSTs. So what we're going to do here is we're just going to add 1 degree to all the SSTs. But we want to do it for all of our MetGrid files so that they can be input into WRF. So what we want to do is we want to use this system function that NCL has, which will let us make a list of all of our MetGrid files. And then we're going to look at how many files we want to read through for our loop using the function dem sizes, which will tell us how many files are there. Next, we're going to run a do loop. We're going to set it at I equals 0 through numFiles minus 1. Again, this is because NCL is a zero-based language. We're going to read in each file one at a time, and then we're going to read in SST. We're going to say SST equals SST plus 1, and then we're going to write it back out to the file. We're going to do this for each file, and it's really that simple, just to like change your field. Now, for example, say you don't want to change the entire field. So, for example, we would want to change all of the orange grid cells in here to match the grid cells around it at the base of Florida. A good way to do that is to do it in your GeoGrid file that you make in WPS. We're going to read in the land use, and then we're going to specifically read in. So we're going to start out by reading the 4 bottom grid cells. Because they're in a square, we can read them out of the array. So 63 to 64 and 83 to 84. And we're going to set those to 7, which will match the blues around it. And then also we're going to get this last upper right orange square directly, 62, 84, and we're going to set that equal to 7. And then we're going to write that back out to land use. And then if we were to view this file again, it would look like this. Okay, next I'm going to show you some pretty basic data manipulation in NCL that you can do with your WRF-out files. So to start out with, we're going to create our new file. We're just going to name it out. We're going to use add file again. And as you can see, we're going to use the C in parentheses there, which creates our new NetCDF file. And we're going to name it T2_dailymax with the date. So what we're doing in this with this new file is we're going to create some maximums and write it to the file that just has one time. So one thing that's really important that I do with every NetCDF file that I create in NCL is I make the time dimension unlimited using the function fileDemDef. If I weren't to make this time variable unlimited, then I would not be able to add more times to the file if I wanted to. And I always want to have that option. It's really important. Next, we're going to read in our WRF-out file. So this is a file that has 24 time steps. So it's just like a full day's worth of hourly output from your WRF run. Next, we're going to transfer our attributes from our WRF-out file to our new dailymax file. So these global attributes are going to be like all of the WRF information, like the domain information and all of the physics options you use. And I just generally like to transfer these with every new file I make so that I know where this data came from. And it's also important for NCL to have this information for plotting, especially the domain information. Next, we're going to read in temperature. And for this example, we want temperature in Celsius. So we're going to read in T2, subtracting 273.15 as WRF outputs in Kelvin. We're also going to read in our land mask and our latitude and longitude and the times variable. To mask out the ocean, which you might want to do to create a T2 over your land, is we're going to use the function mask from NCL. So to do this, we're going to say that temperature over land equals mask, and we're going to point to the temperature variable that we gave it. And where land mask equals 1, we want to keep it. And we're going to mask out anything else that doesn't equal 1. So now to calculate the daily max, we're going to use the NCL function dim_max_n, and we're going to say, look at t, and take the maximum over the 0th dimension, which is time. So we're creating a Tmax for both temperature all over, including water, and we're also going to do a Tland mask with that Tland, the daily max that we created with the ocean masked out. Now we want to write specific attributes for the variable. So we're saying that the 0th dimension is time, the first dimension is south underscore north, and then west underscore east. We're saying the units are in Celsius, the coordinates are latitude and longitude, and the description of our variable is daily maximum temperature at 2 meters masked. Next, we can write out the data just like so to our out file. We write out xlat equals lat and so on until the file is over, and it will create a brand new file of masked temperature, and you can create a plot that looks something like this. Next, I'm going to show you how you can easily read an ASCII data with NCL. So you'll basically give your point to your file name. We're going to use the function ASCII read, and we know how many rows and columns are in this file. And we're going to say it's 21 by 6, and we know that it's all integers, and we want to read it in as integers. So when we actually print that out, it prints out 00 1950, 01 13, etc. And that's how you can really easily read in your ASCII data. So I'm just going to give you an example here. Here's a trajectory of a hurricane that was run in a WRF run. And this is all the latitude and longitude points, and it's sea level pressure, it's winds, it's all that kind of good stuff. So we're going to read in this specific track file. So one function that's really valuable if you don't actually know specifically how many columns there are is we can use the function num-ASCII call of the file name, and it'll tell you how many columns there are. Next, we're going to say that the amount of variables is equal to the number of the columns. And then we're also going to set our contour levels using the function ispan. We're going to set them between 7 and 21 every 1th. We're plotting wind here of the storm, so every 1th knot or meters per second, yeah. So we're going to open our workstation. We're going to name it traj for trajectory. And we're also going to define the color map that we want using gsn underscore define underscore color map. We want to use GMT Panoply. NCL has like probably 100 different color maps you can try. And we're going to also retrieve that color map using gsn retrieve color map from our workstation and call it CMap. So we want to use that a little later in the script. Here we're going to set our mapping resources. So since this data is not directly output from WRF, we need to tell it what we want our map to look like. So these resources that we're setting is we're setting the limit mode, so what kind of map we're going to make. It's a latitude longitude map. And then we're going to do our maxes and mins of latitude and longitudes and our center line of the map we want to make. We are going to make this trajectory using polylines. So we're going to set our polyline resources, and we're going to set our line thickness to 6.0. So it just makes a pretty thick line for our trajectory. And then we're going to set marker resources because we want to put a marker where the storm genesis happened. So our marker size is going to be 9.0, and we want it to be a red marker. And there's our marker resources again. And next, we're going to just draw a map. We're drawing a basic map using GSN CSM map CE, so cylindrical equidistant map. So this map is going to be blank to start out with. And now we're going to actually start reading in the data from the ASCII file. So we're also going to use num-ASCII row, and it'll tell us how many rows, so how many like latitude, longitude points we're going to be looking at. And then we're going to read in that file using the information that we got from num-ASCII call and num-ASCII row, and we're going to read them in as floating points because they are. So we're saying that our latitude, we're going to read all the rows, and our latitude is from column 2, our longitude is from column 3, and the variable, which is the winds, the maximum winds, is from column 7. Now we're going to loop through every point on this trajectory. So what we're going to do is we're going to assign a color based on the input scalar variable. So we're going to assign a color based on how strong the wind is. So the weaker the wind, the cooler the color, the stronger the wind, the warmer the color. So we're going to use this, we're going to set our plot resource for GSLine color. We're going to use this function called getFillColor. For all of the levels, what we're trying to do is assign a specific color to the value of the wind. And then we're going to use the function GSNPolyLine, which we're going to connect the dots with that specific color. And we're doing this for all of the trajectory points from start to finish. And then we're also going to use GSN_polymarker to draw the start of the trajectory, the genesis point. And then we're going to use the function draw equals map. And it's going to create a trajectory that looks like this. And this is really cool, if I do say so myself. All right, so that's reading ASCII data in a trajectory. Now we're going to talk about writing out your ASCII data. So say you have T2 and Q2 at a point, and you want to write them out to an ASCII file. So it's really easy just to write one variable to a file. So you can just use ASCII write. You can name it t2.text, and you're like, I just want to put T2_point in here. You can also do that by specifying how you want that variable to be written. So here it's kind of like Fortran, you type 9.3f, so floating point number with three decimal points. And you're going to write out Q2 point. However, if you wanted to write both of them in the same file, you can do this complicated loop situation where you're putting the data together, or you can also use a function called write matrix, where you can make a data2 equals new, and it's the number of points, the number of times, and two variables, and they will be floating points. And then you write each variable out to the data2, and then you can just use write matrix and write the whole matrix. So you can only do this for a two-dimensional data field. Another really useful thing in NCL is that we can use shapefiles to mask out our WRF data. So shapefile is a geospatial vector data format for GIS system software, and we can use it to mask data to specific region or state borders rather than trying to draw a box over an area. So they can have three different types of data. They can have point data, which is just a location of a city or a point of interest. They can have a polyline, which is something like a road or a river. You can also have polygons, which is what I usually use, which is the borders of a country, state, but it needs to be a closed boundary. And also important is you can only have one data type for a shapefile. So I always go for the polygons personally. So here's just an example of how we can look at our shapefile and see what's in it. So I found this shapefile. It has state borders. I found it just with a simple Google search from the Census Bureau. So what I can do is I'm going to tell it what the file name is, and I'm going to use add file to read it in. So I'm naming it F. So I can just use print F, and it'll write out to the screen the metadata for the shapefile. This is what I get, because sometimes it's just like really hard to figure out what's in your shapefile. So we can look here and look at what variable we might be interested in. So if you look at the list here, I'm probably interested in name. So what I can do next is I can read in the variable name, and I want to see exactly what those look like, and I'll print that out, and we can see that they're names of states. So it's really important to print this out because sometimes there's spaces in the states, like with the District of Columbia, it might have spaces, it might not, or North Carolina or something. Sometimes it does and sometimes it doesn't, and when you call for that state, you need to make sure you're typing it exactly how it's written. Next, I'm going to walk you through an example of how we can use a shapefile to mask some data. So we're going to read in a WRF out file here, and then we're going to open a workstation, and we're going to print it to the screen. So here we're going to read in T2 just at the very first time, And we're also going to read in latitude and longitude. And next we will open our shapefile from the internet, or we're just going to give it a name, shape_file name from the internet that I found via Google. Then we're going to set our options to use the shapefile_mask_data function. So we know the variable name, which is name, and then we also know the shape names, which are Oklahoma and Texas, and those are the states we want to look at. So we can create a new variable, which is var_mask, and use this function shapefile_mask_data to mask that data out. So that is a new variable that we have. Next, we're going to set some plot resources. We want to create a panel plot so that we can, this is actually wrong, not more than one state, but we want to draw the data that we masked, and we also want to draw the outlines of the states. So we're going to set some map resources here, and we're going to zoom in on our area of interest. So we're going to set zoom in equals true, and I also specifically know my X and Y grids that I want to zoom in the area, and I found these just by opening up a WRF file at NC View and hovering over the points to see where I wanted it to start and end. Now I'm going to create a new variable called var_mask_zoom, and I'm going to read var mask between those y start y end and x start x end points. Next, I'm going to make contours, draw them on a map, and then draw the outline of the polygons. So we're going to set some options to true, and we are going to say that we want our contour fill on. Next, we're going to make a contour of the masked area that we created using WRF_contour. And we're going to use WRF map overlays to plot that on top of a map. And then we're going to also draw our shapefile polygon lines that we read in. So we're going to draw the plot mask, and this is what we get. So it's actually pretty cool. So we can see the shapefile boundaries and also the data that we masked out. Next, I want to talk a little bit about using georeferenced graphics in NCL. So here's a pretty basic script. This is one that we went through at the very beginning of this talk. So if you want to add georeferenced graphics, these are the lines and things that you need to change. So you need to load in a new library, a different library. You can only use PostScript, so PS, as a workstation. You need to use this function WRF2geotiff_open. You need to set GSM frame to false, and then you need to write to your geotiff file, and this is important, frame WKS at the end. And then you need to specifically close your geotiff workstation before your script is finished to properly write out that file. So it is pretty easy to link NCL to Fortran and C code. You can create a library from your Fortran C code and link it to an NCL script. You can link pretty low-level NCAR-Graphics NCL to Fortran code and add code calls in the code to code inside Fortran code. You can compile the Fortran code with NCL libraries, which an example is the plotfmt.exe. This is a really much older way of creating plots. We don't really recommend it, but some people still really like to use it. So it is easier to use Fortran 77 code, but it can work with F90 code if you so desire. So one thing you need to do is you need to isolate the definition of input variables and wrap them with special comment statements, which are like NCL Fort Start and NCL End. And then we will use a tool called wrapit to create a .so file. And you just run it from the command line. It comes with NCL, with your NCL binary. You'll just type wrapit and your Fortran script. And then you'll have to load the .so file into the NCL script with an external statement. You call your Fortran function with a double colon syntax, and you must pre-allocate for arrays. in your NCL code, in Fortran code. Here's an example. So here's a very simple subroutine to compute TK. And this is pre-allocating for arrays. And these are the wrappers that you need to use, the NCL Fort Start and the NCL End. That's what you need to put in your Fortran code. And then next, you want to run wrapit of your Fortran code, and it creates a .so file. And then you will load it up where your libraries are loaded before your begin statement with external mytk, and in quotes, your .so file. So here we just have your NCL script. You're going to read in WRF user getvar of t, and you're going to read in pressure, and then we're going to pre-allocate space for your output arrays in your NCL code. So that's what we're doing with this tk equals new, and it's going to be the dim sizes of temperature and the same type variable as temperature. Now we're going to call the Fortran code. So one thing we have to remember is that Fortran and NCL arrays are ordered differently, so we're going to put them into the Fortran code opposite of what we would normally do. So how we do this is we put mytk and then the double colons and then compute underscore tk with tk will be our output, and then our inputs are pressure and temperature, and then the array sizes are, we're going to have to go opposite. We'll go dim of 2, dim of 1, and dim of 0. And you can use simple Fortran 90 code, but it can't have any of the following features. You can't have pointers or structures as arguments, no missing optional arguments, no keyword arguments, or recursive procedure. So if you are to be compiling your NCL from source code, these are some important things to know. You might get these errors, and these are the libraries that you need to make sure are in there. So I really don't recommend unless it's absolutely necessary, but really just use the binaries and don't use source code. All right, so I'm going to close out this talk talking about a few additional packages that are really useful and will be really useful for use with WRF data. So WRF-Python is another collection of diagnostic and interpolation routines for use with WRF ARW developed here at NCAR. And it's very similar to what is provided by the WRF NCL Functions. It was actually written using the WRF NCL Functions. So when you couple this with either Matplotlib or Pingle or Pineo, you can create plots that are very similar to what you can make with NCL. It's still in development, and you can find information on it at this GitHub site here. Next, another thing that's being developed here at NCAR is Geocat. It stands for the Geoscience Community Analysis Toolkit, and it's a collection of Python tools related to NCL developed here at NCAR. So one thing I didn't bring up earlier is that development of further NCL capabilities has stopped here at NCAR. It's still in maintenance mode, so bugs are still being fixed, and it's still going to be supported by NCAR. However, NCAR has decided to move more towards Python. So they created this Geocat, which will take a lot of tools that are only available in NCL for the geoscience community, and it'll create new functions in Python that you can use. There's an examples page, which is somewhat similar to the NCL examples here at Geocat-examples, and then also updates on the progress of Geocat can be found here. Finally, if you need help with NCL specific to WRF, you can use the WRF and MPAS support forum. This forum, if you're using NCL, this forum is only used for questions about using NCL with WRF. If it's not a WRF specific NCL function, you need to go elsewhere, which is ncltalk@ucar.edu. So in the WRF and MPAS support forum, there is an NCL section in the post-processing/utilities folder. and you can type your question there and it will be answered by me probably. So thank you so much for your attention, and I hope you have a great tutorial. Thank you.